So I'll start sharp at 2:10. Yeah?
Yes.
Wait for a few more minutes. Did you have a chance to review the assignment that I had loaded?
Very briefly. I didn't read it in a detailed way yet, but yeah.
Yeah, maybe that's why people got scared that they may not have reviewed. And since they had asked, made that a prerequisite, so maybe they had shy of doing it. But since you're here, I'll make your time worthwhile. And so let me go through that and see. So let me start then, okay? So I just want to summarize what we have covered so far, okay, to get stock of things. And please, since you're the only one, you can ask questions anytime. So we started by defining a formal semantics for programs. We did it in two different ways. One using the transition as transition systems. Then we defined it using in a bit more detail. This was somewhat low level. So here we also looked at the structural operational semantics, where it was the set of execution traces denoted by the program were defined inductively over the structure of the syntactic structure of the program. Then we introduced core logic as a specialized logic to reason about programs, okay, using purely based on the structure, okay, so that we could reason about all possible execution traces using predicates, okay, pre and post predicate. Then we saw how to construct a proof using the inference rules of Hoare logic as a tree of Hoare triples, where each Hoare triple was derived by the previous set of assumptions using by instantiating the inference rules. Then we were looking at some automatic software verification methods. Specifically, we started with straight line programs. Okay, who has joined? Oh, so hi, Anli.
Good afternoon, sir.
Yeah. Okay, I was just recapping, what we had done so far. Okay. So, we started looking at straight line programs, okay? And those were, and the way that I approached it was as though, this was a method, could be as a way to consider how to mechanize and automate application of Hoare logic construction of proofs. Specifically, we looked at the backward and forward proof for straight line programs. So the backward proof consists of strictly applying the assignment rule backwards from the post condition to the precondition, and showing that the assumption implied the weakest precondition derived, and the forward proof pushed the precondition of the program forward, computing the strongest post condition at every step, and then getting the strongest post condition for the entire program. We saw that how this forward proof could be viewed in terms of the SSA formalism, okay, and that where each the result of applying the forward assignment rule after each thing could be written using the SSA formalism with time-stamped variables, which you needed anyway to eliminate the existential quantifiers. And we saw this automatic method for straight line program consists of two steps: converting the program to an SSA formula and generating an appropriate verification condition, which could be solved using an SMT solver. And we saw that this was worked for straight line programs, and this would form the basic unit for method called bounded model checking, which we also saw, as a way to handle, conditional programs as well as loops. Okay. Now, then we address the issue of how to do verification of programs with loops. First, in terms of core proofs for loops. Hi, Dhruv. Are you there, Dhruv? I guess he doesn't want to say hi. Okay, so and one way to do is to using the crutch of inductive loop invariance. So what inductive loop invariance were, and how a whole rule for loops, which way to derive whole triple for entire loops using loop invariance. Okay. And then, along the way, we also saw bounded model checking as we introduced bounded model checking as an incomplete but automatic method for verifying program with loops. And before I get to that and talking about unwind program, what I want to show you is this SSA formalism, this verification method using SSA for straight line programs. Here I compared it to a way of, you could say, a way of applying the forward assignment rule, okay, for every statement in the program. But there is another way to view that as well. Okay, and this sometimes, that's why this verification method using SSA formalism is sometimes called symbolic execution of your program, as opposed to executing a program on a single input. Now, whole proof, etc., is one development, one way of handling, describing the logic and then creating proofs. But research in compilers, the community, they were also simultaneously trying to address this problem of verification. So there was, so this kind of symbolic viewing that proof, the forward proof, more as a symbolic execution of program. That's the, can also be viewed, and that's the concept that I want to introduce, which could be applied for straight line programs as well as, condition. For example, why do we call this SSA, method of verifying the symbolic simulation? So for example, so this is how you can start with at each point rather than, so it's symbolic in the sense you're executing not on a single input, but a whole set of states or inputs or states that satisfy a predicate, okay? And as you execute the program, you're pushed. I'm just giving you, this is another way to view the construction of proof using forward assignment proof. And you can see the similarity with SSA. So after you apply and after executing the first statement, you get the set of all values values for the program can be characterized by this predicate, y naught is equal to 1. After that, you have a condition, okay? Now, condition is like making execution under that assumption at that point, okay? So you m not greater than 1, and then you apply it. So for the time being, you assume that the state after execution of 1 satisfies this condition, and then you move along. So as you can see, each of these is exactly what we defined as an SSA. Once again, whenever you get if you don't have conditions, you have strict straight line program. But what I'm saying is this can also be used for conditional, as we also saw. There you will encounter these conditional expressions, okay? And then you make that assumption, then you and then you go on. And then what you get finally is, and then of course, because if it's a strictly straight line program, you only get one path through the thing. Now here it is a branching program. Therefore, you will have to consider the other valuations for these expressions, Boolean expressions that appear as conditions. This particular symbolic execution path, okay, was under the assumption that both the conditions that you see here were true. Okay, so in that sense, this can be considered as execution of the program on predicates, okay, that characterize whole set of states. And once you have these things, then you can solve, and this can be viewed as formulas, and then you can answer questions about whether a particular assertion is met or not, okay? So do you understand the point I'm making, how you could consider this as symbolic executions? Why do I call it symbolic? I just want to see if you understood, okay? What is symbolic about this execution? Dhruv, can you answer?
We are not delving into the semantics of the execution.
No, I think this, no, say that again. So you are not delving into the semantics. That's, that's
so integral semantics.
No, but more importantly, the analogy that I was giving was, see, you're not executing it. See, after every execution, you're executing on a whole set of states, okay? That's why, and that set of states is being represented symbolically as a formula representing the predicate, or expressions, if you want to call it. It's actually a predicate at each step. The value that you get is possibly a set of values that you would get. So you're executing it over a set of values, that is one. And what and those set of values that you get after executing each instruction, basic instruction here, is represented symbolically as a formula, and it's in that sense this can be considered symbolic execution. Of course, if your program has multiple paths, then you'll have to explore each possible path. Now, for example, here this is the first, so where here this is the case where the first condition, those situations, those scenarios where the first of the two condition is true, but the second is false. So if the second, those situations in which scenarios where the second condition will be false, I mean, if the state that you encounter after line 5 such that the condition on line 6 will be false, then this is the execution path that you would be
So
taking.
I don't understand what's symbolic about this. I mean,
Yeah,
aren't the formulas the same as the formulas in the program?
Compare it with if you were executing on a particular input, say starting with y, m, and x and n taking specific values, 0, 1, 2, 3, etc. Then you would get specific values after each statement, okay? And instead, here we are executing it by representing the result after every statement as a formula that represents the set of values that you can possibly get at that point. That is what I mean by symbolic.
But the formula looks exactly as the program, right? There it was m greater than 1. We have the same formula, m naught.
That is true,
1.
but m1 equals m naught by 2 is not exactly the same as it is true that, so it is, yeah, that is true, but there is more things here. Nah? So here you could get the value that m on the left side can take are any values that satisfy this condition. M1 equals.
But that's that's kind of declared by the statement m is equal to m by
That
2
is
itself,
true.
right?
Of course, I'm deriving this from the statement. But the important distinction to make is at each point, rather than saying exactly what the value of m will be or the various values will be, I am carrying along the entire state. I mean, a set of states, okay, which is being represented by a symbolic expression. Okay.
So do you mean to say that in particular, rather than taking the values of the variable themselves, which would be actually part of the execution in a real program where the user defines values for the variables, we keep the variables abstract and symbolically proceed the program?
That's right. No,
and then argue about the
I'm
form.
still, you're missing the point. Okay, I keep emphasizing. So instead of values, I am calculating an expression that denotes the set of all values that could potentially, that can result after line 4, for example. Okay. And I'm keeping tab of that. Okay. That is the distinction here. So after this, I will, yeah. So here after this, what M1 could be taking, so because M could be taking so many different values, okay, at this. So, and contrasting this with the execution, if you track specific values as opposed to set of values, okay? That's the distinction. Yeah. Okay. So
yeah, that's what I mentioned, right? In the execution, the user would be providing some values for M because otherwise the program can't execute.
Yeah, yeah. You know what the user, I mean, the user or whoever. Okay. When you analyze, when you run programs, you're executing on specific inputs. Here, the SSA could be viewed as a symbolic execution. That is the analogy that I'm making. It is as though you're executing the program over expressions that denote sets of values. Okay, then you could, one way to analyze for all possible, because verification here is, goal is to analyze it for all possible values. Okay, you could run it for every specific inputs. Instead, we are doing symbolic execution. Okay, so that's the distinction that I'm making. So, but here there is one issue of how do you deal with expressions? I mean, Boolean expressions which create branches, and for that, then you will have to say, oh, I will split whatever state that I get after line 5 into situations where those values for which this expression, I mean, here, for example, after line 2, m is greater than 1, and is true, or m is greater than is false. Okay, so that's the kind of thing. So the third one is one in which both those scenario represents those scenarios in which the even the first condition is false. The first condition is false. There's no question of executing the rest of the program at all. You'll be at line 1. Okay, so these are the three. Any sequence of states that satisfy these predicates will be a actual execution path with the actual execution path. So in this way, I have split the set of all executions into 3 symbolic executions. Okay, three symbolic executions, because each of these symbolic execution path represent a potentially infinite set of actual execution paths with actual values. That is the distinction that I'm making. So you could view this in that in that sense. Okay, so yeah, so and yeah, so this is what kind of the automation of the whole proof in SSA can also be viewed as. So then the question is, each of these is a path, and now you could this itself is a formula. Okay, like you have observed, and then if you want to show that at the end of the execution path, a certain condition or certain property holds good, then you could say that the conjunction of these conditions implies a post condition, and so each of these will give rise to a verification condition which can be discharged. Okay, that is another. This is kind of a it's the same thing as what we did. So in this case, for this program, because it had there were three symbolic parts for the different possible valuations for the expressions in the that appear as in the conditional statements. Therefore, now you could use this method now as a way to address loops. Okay, so for example, so that was the objective of this problem 2. So what you can do is, let me get the for example, the program that's given the same program that I had here had the CFG. Okay, so you could, for example, enumerate the different parts. Okay, so for example, there's one, since here, one way to handle loops. This was the motivation for bounded model checking. Okay, where you enumerated the all the parts. So here, this is the CFG, which is just the control flow graph representing this program that I have here. So one way to verify is like we did in the for the if then else program. You could get symbolic execution paths for every path up to a, you can enumerate all the paths. Obviously, the number of paths here will be infinite. So, if you want to do bounded model checking, which was what, then you could enumerate the paths up to a certain bound. Once you enumerate a path, then you can convert them into a particular formula, and then you could deal with it. Okay, so that is one way that you could verify. Where am I? For example, here, so there's one path here based on the condition. Okay, so that takes S from S0 to S4. Okay, and for that you can generate the symbolic expressions that you do by generating using the SSA formalism, and then you can then convert that into a verification condition of this fashion for that path, the path in which you don't enter the loop at all. Okay, and then you go directly to S4, and that's what is represented by this symbolic path, and the corresponding SSA formula for that is this. And then that can be used to prove, generate a verification condition and then prove. And then you could generate all possible paths up to the k. That is the idea, pretty much, of bounded model model checking. Okay. Okay. So let me go back to my thing. So what's the problem with this approach. Okay, so that is, you would have an exponential number of paths. For each path, you can generate a VCC. Okay, a verification condition, and you could you could do that. Okay, so the problem is that you have an exponential number of symbolic execution paths for you to consider, because for each iteration you can have as many possible different, if there are n expressions, branching expressions, you obviously it gets multiplied by those things, and therefore you get the number of verification conditions that you have to generate will be infinite. Okay, I'm sorry, it will be exponential. Even for a bounded k, the number of paths will be exponential in terms of the depth for which you will have, and that is the disadvantage that we are trying to avoid by using this idea of merging. Okay, that itself was a way of implementing the conditional forward rule, because the whole proof does not do this. Okay, because it does use this conditional forward rule to kind of combine the two branches right at that point. Okay, so as the idea here is the following. Okay, to avoid that combinatorial explosion. So what I do, which we already kind of saw, is to do merges here. Okay, rather than consider the different possible Boolean, truth values of these expressions as separate things. This is how we will embed that in the symbolic expression generated for the code itself, for example. So here, by introducing these new merge variables. Okay, and if you look at it, this is exactly what the conditional inference rule does. So at this point, for example, there is a merge point. After every when you get out of a conditional statement, there are two merge points, one corresponding to the inner if, and the second one corresponding to the outer if. So there, what you can do is you can now generate a symbolic expression that merges the set of all values that you can get if you took the two different paths. Okay, actually four. At the first point, at the first red merge point, you would represent. So this is what represents that. If n is greater than or equal to m, you could get either n1, which there are two possible ways to reach this merge point. So you will create a symbolic expression corresponding to both those values. Okay, both the possible values that you can get by traversing the two possible execution paths. Okay. Similarly, there is another merge point corresponding to the second loop. So for the first one, you will have to generate. You have to generate one merge for every variable that can potentially gets modified in that conditional statements. Similarly, here in the second one, so you generate one for m, n, and 3. Now, if you had this kind of a symbolic expression that takes care of the the if-then else's through merging. Now, if you embed this that's the idea. Through introducing these merge variables, you before you do the before you even enumerate all the paths corresponding to the loop. You generate an SSA in this form, so that then if you had a program of this kind, for example, if you went back to my this one. So for this program here, now instead of enumerating all the paths over all the iterations, I would generate an SSA with merged thing. Then what will happen? Of course, I'm introducing new a bunch of new variables, but then this unwinding of this loop can be performed in terms of by just because there'll be just one symbolic path that merges all the conditional parts into one, and that's why when you then unwind this merged symbolic path over all iterations, your size of your expression that you get, okay, you'll still have, you have to consider k different unwindings, but each of them will be, the size of that will be only linear in the number of iterations in k, opposed to splitting and then enumerating all the parts. And that's what that's the idea of that is used by So instead of enumerating all the parts, that you can take up to k, and that's the advantage that it has. Now this is the one that I guess Dhruv asked, okay, is that clear now as to how you're avoiding the combinatorial explosion that you would get by if you enumerated all the parts? Specifically, Dhruv,
did I ask this today?
Yeah.
Okay, I think this. Okay, yeah, sure, yeah, this answers the question. I mean, I also would like to comment that this also passes the work onto the SMT solver.
That is true.
Or the SAT solver that is being used.
You're right. So what happens is, this one, your expressions are more complex. Yes. The conditional branching is now embedded inside your symbolic formulas that you're getting it. Okay, that you're generating. Yes. Although over all iterations, the size of the formula that you get for k, it does not, is linear in terms of this slightly fatter formula. Okay, it's fatter because your symbolic expressions now have conditional expressions. That is true, but the hope is that SAT and SMT solvers are able to handle, okay, these kinds of things quite efficiently through their heuristics. The DPLL algorithm, etc., will have to do the k splits. After all, when you have a conditional expression, it's equivalent to a clause, okay, in that, and the DPLL, along with the various heuristics and CDCL, etc., that we saw, the hope is that it is able to solve this, more efficiently, and that is the idea. Because there, in your previous method of enumerating all parts into unwinding into straight line paths without branches, you are, at the start itself, you have infinite number of, exponential number of paths. Okay, so yes, so the hope is that the SAT solvers are able to handle that. So that is the idea here. Okay, so, and this is what I want you to, the problem 2 addresses, okay, just to contrast this one. And I wanted you to actually use CBMC using the show VCC thing to explore how it generates this merged version of SSA. Okay, I want you to do that. I want you to do it on your own, but I will show a little bit since I've already run. So I'm going to be conducting this a little bit like a tutorial, okay, on this particular program that I have here, okay, to see what exactly, I mean, I've already given you an idea of what this merged thing is and how it generates, okay? So that I'm going to show you next, okay? So, before that, are there any, are there any questions about this merging of the thing? So maybe you can see those examples, what exactly the CBMC generates. I don't know if any of you had a chance to explore that show VCC. Did any of you do it? Yes, no?
No, sir, I didn't try.
Okay, so then let's shift gear here, and then I'll show you. Then I'll spend some time so that then I want you to go through these. The first part, these three problems are kind of exploratory. I'm going to be discussing it here, but I want you to redo it anyway so that hopefully those some of the points that I'm making will sink in to your yes. So this is the program that I'm analyzing. Okay. And let me start with okay. So you can see this thing, right? So this is the program. Okay. So what I want to see, unwinding of these things can be represented by these things. For example, for k is equal to 1, this is this is one way to represent the result of unwinding. Okay, and for k is equal to 2, so for k is equal to 1, it unwinds this thing for just the body by 1. Here the body is this one. Okay. And what is this whole thing? Sorry. So from here to here, and the body has a conditional statement, and but you get out after just one unwinding, and so you get, and then you have to check the assert. This is yeah. So this is the effect of unwinding it once. Okay. Yeah. Okay. So it unwinds the body once, and it gets out. Okay. It gets out. See, but then yeah. So if you unwound it for k is equal to, this is how CBMC unwinding works. You could say that this one is actually kind of equivalent to 0 unwinding. Okay, because you're exiting after even before, although it unwinds. It unwinds the body once, it kind of exits, by checking this one itself. So you will see that k is equal to, if you do unwind 0 and unwind 1, it is pretty much kind of exiting after that. Unwind 1 will just unwind it once, but although the exit condition is after just 0 unwind. For k is equal to 2, it unwinds it the body twice, but it's as though, yeah. So the effect is it takes care of those situations where you could be exiting the loop after a 0 iteration and after 1 iteration. So you could now see what the so what I want you to do in this thing is, so this is kind of the effect of representing the unwinding as nested conditionals. And I want you to do run CBMC, not verify these things, but actually using show VCC on these nested conditions to understand how it generates the SSA and the VCC. That will illustrate very clearly how the merging works. Okay. Okay, so that's what I'm going to illustrating to you. So let's see if I have, yeah. So for example, I'm going to show, yeah, the actual unwinding that I've given here, unwounded nested condition, is slightly different than what I'm showing here. This one that I showed here exactly corresponds to how the unwinding is done in CBMC. So if you did a show VCC on this code, okay, then this is what you get. Okay, for a moment, ignore this. This is for k is equal to 1, okay, for this program, okay. This is the VCC that it gets. You should read this as this is like a inference rule, assuming all the atomic formulas above the horizontal line, which is the SSA part, which I keep calling as the SSA, implies this one. Okay, that is the one that you're trying to prove. Okay, so and this is exactly the VCC that it generates for this program. Okay. Which is corresponds to the unwinding of k is equal to 1, represented as a nested thing. So let's try to read this, okay? And I will show you where the merging happens and how exactly it computes. Now ignore all the junk that you've seen here. Hey, Diganta, you're there? See here? Diganta? Oh, he's unmuted. Okay, so I don't know. Did Diganta show you this VCC? Is this the VCC the first time that you're seeing it, or was it shown in one of the tutorials that for CBMC that Diganta conducted? Hello.
I think this is the first time that we are seeing it.
Is this the first time you're seeing it? Please.
Yeah, for me. Yeah.
Okay, so yeah, so the real stuff starts from -12. Okay, so you can see, ignore all the number that follows after the hash symbol here. Okay, that is the timestamp. Okay, so just ignore this gibberish after the exclamation point, okay, that has a different meaning. So here there are 3 variables, I, X, and Y. They have some initial values, which is denoted by hash 1 with the timestamp 1. Okay. Now there is what I've not shown here is there is so there is an initial condition here. Okay. So there is, initialization of I, with I is equal to 0, and that's what happens here, okay? So that's the SSA generated corresponding to the assignment I is equal to 0, and it increments the timestamp by 1. So, this is I hash 2, okay? And now you can see that it generates 2 guard variables because there is nested conditional here. So there's guard 1 and guard 1 corresponding to I less than or equal to n. And that it generates by plugging in, n is greater than, I is less than or equal to n, which is represented as n is greater than or equal to 0. I'm sorry, not 1. So n1, you should take it as n hash 1 greater than or equal to 0. That's guard 1 and guard 2. So it keeps track of all the guards as it generates the SSA. Guard 2 corresponds to this thing. Okay, x is less than y. It is representing it as the negation of greater than or equal to 0. The important thing to notice is the timestamp, okay, that it uses. It plugs in the latest timestamp version of the variable in that expression, because that's what is needed to represent. That's the condition that is represents the actual condition on the values that exist at that point. After that, it is generating the SSA for the individual assignment statements. Okay, in the then and the else branch, and that's what is happening here. Okay. I mean, you have to stop me if you have any doubts or questions, okay? So, and then here is the merge, okay? So now there is, this is the first, this is the first set of merge symbolic expressions that are generated corresponding to when you're getting out of this thing. So there's I is equal to 1 is, where is I is equal to 1? Okay, I being assigned 1 is generated here, and these two are generating the merged symbolic expressions for the values x and y. So it says if guard 2 is true, that is if x is less than y, then the value, there's a new value. The merged value has the timestamp 4 is 2, otherwise it is 3. Okay, there are some extra timestamp variables it generates here. Okay, you may ignore that. I mean, there is some technical reasons for that. I don't want to get into that, but effectively it is saying either it is the initial value or the new value that you get. So notice that x3 is x2 is x plus 1, x1 plus 1, and that is the same as x3. Okay, so these are the merged symbolic expressions that are generated to define the values for the newly introduced merged variables. Okay, and then you have a merged variable for these, for the outside conditional expressions. Wait a minute. Yeah, I'm sorry. What is guard 1 is n? Oh, these are the merged variables. I'm sorry. Yeah, so with k is equal to 1, you see there is no need to generate a merged variable. You're not even here. Okay, if you were at this point at where my cursor is, then you would have generated. The assert is right here within the else branch. Therefore, what it is, it doesn't have to. It's there. You don't even get the merged, the outside merged value, and therefore you see that the assertion is generated, and that is because see the else branch, the context, that is the context in which this assert appears, is under the negation of this guard. Okay, notice how the formula corresponding to the assertion is generated. It is conditioned with the context that applies for at that point. So what it is, so because this assertion appears, you need to verify this assertion only under this else context, okay? And that is defined by guard 1, okay? Which is negate I less than, which is thing, and that's why it generates the assertion. It tags the context corresponding to that assert statement. Okay, so that is important to observe. So what? Yeah. So in other words, so is this clear? Why you have both the merge thing and this, why you need to attach, you also, of course, you'll have to plug in the latest, the timestamp variables, the latest timestamp variable that occurs at this point, which happens to be x5 and y4. In addition to that, you will have to have attach the guard, the context that assert appears in as the precondition. So any questions here?
I just have one question. So
I'm sure you haven't understood the whole thing. There must be some question. Why don't you ask?
yeah, so the else condition on, so the latest value of x and y in the else condition should be x1 and y1, right? But it has introduced x4 and x5 and y4.
Forget about it. So if you notice that, say x5 is the same as x1, okay? y4 is the same as y1, okay? So effectively it is x1 and y1, right? So if you exit here, so what the latest one is in terms of x1, but as I said, it is introducing a set of new variables. There is some redundancy here, and there are some technical reasons for that. I don't want to get into that, okay? But effectively, it is getting whatever the value was, the timestamp variable prior to this if then else, which is what you will have to get, okay? And the another important thing to notice is that this assertion has to be proved under the under the context that is associated with that statement. Therefore, there are two things several things that are happening here. So let me get to that. Let me get to this thing. So I have the list of things that you will have to. So here is. So important points to keep in mind and observe about SSA and BC generation. So first is guard conditions are generated and maintained for every conditional arms. And later you will see, including loop conditions, because here the loop conditions, when you unwind it, they are converted into if then else, okay? So it will generate for loop conditions as well, okay? So that is one. And number two, every basic SSA, including assert, has an associated context, which is implicitly maintained. Because see, by context, I mean the actual guards, okay? For example, this first if then else introduces one context, which is defined by I less than or equal to n, okay? And that is scoped because, obviously its context is scoped. Therefore, every, the basic statement, the assignment statement here, has an associated context. For example, x is equal to x plus 1. That assignment, what is the context of that, Siddhant?
If x less than y.
No, it is both I less than or equal to n and x less than or equal to y, okay? So see, it is accumulated context, okay? So it is, so you will have, because that's why you have to be careful. The context is scoped, because if you're here at this point, the only way you can be there is if both these conditions are true, okay? So it is the conjunction of all the contexts that this assignment statement, all the nested context that this assignment statement appears within the scope of. Okay, that's how it is. It's generated, because that's what determines. So for y is equal to x and the leap, what is the context there? It is
It's I is less than or equal to n and negation of x.
exactly right. Okay, so now for I plus plus, okay, who shall I ask? Who's there? Chandradeep. Okay,
It's only I less than equals n.
I less than or equal to n. But how is that determined? See, what happens is, as a result of, at this point, these two contexts get merged, x less than y and the negation of it. And therefore, it doesn't, this scope here doesn't contribute anything to the context here. So it's the context of that. Although it is not explicitly shown in this VCC, internally, the SSA generation method does maintain that context for everything. Similarly, the assert also has a context. Harsh, if you're there, so what's the context for this? Yeah, it is.
It is this thing: if x less than y equal x equal to else x equal to y.
Yeah, think again, Harsh. This else is
okay,
actually
yes, the first thing, lol.
So it is just this guard,
Yeah.
as it is evaluated right in the beginning, and that's what is the context associated with this. And what it does, that is the second thing that it maintains. Okay,
Nice.
and the third point is contexts are merged with the in the merged variables for conditional statements. Okay. And that's what happens in these merged variables. Okay, so finally, the VC for an assertion is generated first by instantiating the variables in it with its latest time-stamped versions. Okay, at that point, and conditioning it with the corresponding context. Okay, you will have to do that, because if all the contexts are merged, if your assertion is at the very end of your program, by which time all the contexts would be merged, and the only context will be whatever the initial assumption is. Okay, so if the assertion is the post condition is at the very end of the program, then you don't need to maintain these contexts for everything. But since CBMC allows the possibility of the introducing these assertions, annotating assertions at any point in your program, you will have to keep track of the thing. But you will have to keep track of the context anyway in order to create the that's the reason it does. Okay, so, and that's why this assertion has to be, the meaning of the assertion is, if that is true, what you're expected to prove is if that assertion is true while you're at that point, okay, at that location. And then you see in SSA, unlike in the transition system formalism, we are not maintaining PCs, okay? If you're maintaining location as explicit part of your state, then you don't need to maintain these contexts, okay? So here, and why unnecessarily maintain this PC and then increase your set of states in any case. So SSA, the idea is not to maintain PCs, and therefore you will have to maintain context, okay, in order to generate, and then you will have to precondition the assertions with those things. So these are the three, four important points to observe, okay? Yeah, I think I have, what's the time here? Okay, I'll take another 5 minutes. I think somewhere I have the thing for this as well. So let me quickly show that. It's too complicated. Okay, so let me not. Yeah, maybe you could try doing it for K2. So K2. So let me. So here it is for K2. So K2 has two assertions, correct? So why does it have two assertions, Dhruv? Is Dhruv here or is he left? I think he has left. Okay. Dhruv is not here anymore. So therefore, I'll go to Siddhant. Okay. We'll start
Because a loop body will run twice if the unwinding
twice, and I'm showing the kind of the effect of as nested if then else. Okay. So this corresponds to iteration 0. This corresponds to iteration 1 after executing it once. So that's why. So what I've shown here is the okay. Yeah, this is actually for the second one. Okay, and you can see. So there are three things you can observe here. So there are two merges. Okay, I mean two merges here. One corresponding to this as well as this. I think so. Actually, there are a lot of merges. So there are one merge for this. Okay, actually the merges are for this one and this one. Okay, and there are two merges. And important thing to observe is that the guard for this one. I mean, the guard for this one is just I greater than or equal to 1, which is guard 1. Okay, that's what this thing is generating. And so that's simple. But here is the VCC generated for this assertion. Okay, the context for that, Siddhant, is what is that? It is the else corresponding to this. Okay, it is still under I less than or equal to 1. Correct, Siddhant?
Yes, the I less than equal to n, and then the second I less than equal to n, and the negation of the x less than y.
No, it is no. So this one is this else matches with this if. Okay, with if, and therefore it's just this and the negation of this. Okay, because it does not occur in this. By the time you get here to this else, the context of these two things are merged anyway, of this if then else. Okay, that's why you don't need to consider that. But of course, so that is merged into the new variables that is generated anyway. Okay, so although see, you can reach this point through either executing this arm of this if then else or this arm, but I don't need to worry about those two things because they would have been merged right at this point. Okay, at this point, which is what one of the merges here indicates, and therefore it's enough to just consider for this assertion only those contexts that are relevant, that are alive, that this particular statement is within the scope of. Okay, and that's what this you can see this condition says. That is guard 1, which corresponds to this I less than or equal to n. See, in the program, both are I less than or equal to n, but the guard 1 and guard 3 are expressed in terms of different timestamp variables. This one in terms of n1, which is the initial value. The other one in terms of n and the later I. You also note I is there is So CBMC does a lot of optimizations even before the thing. Okay, it's getting late. Okay, so let me quickly. So there's all these things that you normally expect compilers to do, like constant propagation and all these simple things it does. Even prior to generation of the VCCs. And that's why you might be surprised. See, although I'm doing I is equal to I plus 1 repeatedly, what it is doing is it already propagating those constants with I is equal to 1 and I is equal to 2. Okay, so it does constant propagation, and that's why you're getting the thing. So I think I'll stop here. Okay, and I will continue next time. So please do next time, by the time we come, it'll help, for me to go faster. If you did a little bit of what I asked you to do, which is what I'm asking you to do is to take the loop code, do unwinding and generate VCCs for that, which is what I'm going to explain, and do that. And yeah, so you'll have to do this assignment anyway. So just do it. Specifically, what I want you to do is this problem 2, okay? And here I'm adding that you also try and generate the VCC for different unwindings for this code that I'm showing here, and compare that to your if then else nested if then else code, and then come ready for discussion on whatever. Okay, so this is Chan. What's the question? Did you really, Chandradeep, if you're still there? Okay, so if people want to leave, they're free to leave, okay, because it's getting close to your next class, possibly. Did you do unwind 33 or 3?
33. There was an exam assignment problem 3 or something, right? With 2 to the power.
No. In order for you to unwind 33, if you literally did 33, of course it will be mind-boggling. Okay, that's why I specifically asked you, maybe unless I had a typo, don't do. I mean, beyond 3 becomes not possible for humans to read. Okay, so in order to understand this merging and the guards and how SSA is generated, and how the contrasting between the if then else and there are certain things that happen differently in the case of loop, and that's what I want to bring it up. Just do for 0, 1, and 2. Okay, I think up to that you can, as a human eye can still read it. Okay, try doing it for 0, 1, and 2. At most, and see how it compares, the loop unwinding and the nested if then else. Okay, I will continue this on Thursday. Okay, see you next Thursday. Bye-bye.
Thank you, sir.
Thank you.